the man who leads from the front. With a virtual round of applause on the screen, coming up is Anvit KS.
Hello, hello, hello. Good morning, everyone. Good morning, Fatima. Thank you for the lovely introduction. Ladies, gentlemen, and others, it is my great pleasure and privilege to introduce my partner in crime for today, the classy, the creative, and the mesmerizing, your virtual host for the day, Fatima Lokhandwala. Hello, Fatima.
Hi, Anvit. Good morning. How are you doing today?
Absolutely brilliant. I'm just excited for the next, the sessions that we're going to be attending today at VLD Summit 2021.
So, Anvit, while we begin our day two, I think it's very, very important for us to go back, do a little recap of what happened on day one. So, over to you, Anvit.
Absolutely. So, just to give you an idea, Huawei Technologies India Private Limited, in association with ACM India, has brought to you this two-day online technical research summit, Very Large Data Engineering Summit 2021. Day one covered the latest research and industry challenges, cases, and sharing on areas of low resource language, natural language processing, natural language understanding, ranking, knowledge graphs, and recommender systems. We also covered advancements in large-scale multilingual models, deployments, challenges, intelligent operations, and site reliability engineering. We had over 13 sessions and a panel discussion by our esteemed speakers. Some of the highlights of the day: we had an interesting keynote on causal video inferencing, throwing light on the way to the future of video relationships, understanding and inferencing by Tansek Chua. Session by Dr. Manish showed us the huge problem space of messy data generated by humans, harder part of modeling behavior, and even harder to influence it in true Indian context. We also had sessions on exploiting multilingual models, language relatedness, merged models, transliteration and translation in handling low resource language. Zero-shot improvements of Mural, Mural Large, Relate M, information extraction using unsupervised way are some of the key forwards from the sessions of Professor Partha, Professor Mawsam, and Professor Sunita.
A lot was covered on biases, ethical challenges, multilingual content security at large, with way forward in discussions by Professor Animesh. We had a panel discussion by Professor Abhijnan, Mr. Devdut, Professor Animesh, and Mr. Kwan. Professor Dilip and Dr. Rajiv Rastogi shared practical use cases and experience of data annotation, noise and input, leading to challenges and various techniques of cleaning and model deployment and good practices. This paves a good way for real life using explore and exploit to continuously coverage to the business goal. Sharing of Mr. Hupong was quite insightful with regard to large-scale service deployments and O&M in an intelligent way using AIOPs. Well, ladies and gentlemen, day two is dedicated to advancement in multimedia frameworks, pipelines for consumer devices, and how the modern computer systems and system AI are answering the grand challenge problem of data store. Over the course of this day, we will have 11 highly insightful and informative and, of course, relevant sessions. So with that, ladies and gentlemen, it's now time for all of us to roll up our sleeves and get ready for day two of Very Large Data Engineering Summit 2021. Well, if all of you are ready for day two, I want you all to quickly go to the chat box and type in READY, ready. Let me see all of you quickly devoting yourselves to the chat box, typing in ready. Give me the landslide of readies in the chat section, ladies and gentlemen. Post that, we will be beginning and commencing day two. Well, I see we've got a lot of readies coming in. Keep the energy flowing in, ladies and gentlemen. This is day two of VLDE Summit 2021.
It's time now for us to bring our first speaker on your screen. And we have with us Mr. Olivier Crête, who's been involved in open source software since the year 2000. He's been involved in Genome since 2003 and in Gen 2 from 2003 to 2012. He currently works for Collabora Canada, where he leads the multimedia team. He's been an active GStreamer developer since 2007, first working on the VoIP and video calls, but lately he's been working on all kinds of multimedia projects, particularly around the embedded platforms. Here to speak and give us an introduction to PipeWire is Mr. Olivier Crête. Over to you, Olivier.
Thank you. Let me share my screen and hope the technology works.
It works.
Yes, finally. So I'm Olivier Crête, and I'll be telling you about PipeWire, which is a system to exchange multimedia streams within a computer. PipeWire itself started before PipeWire. There was something called Pulse Audio. Pulse Audio was a daemon to provide mixing and other features required to make use of the sound cards that are in modern computers. By modern, I mean really from 15 years ago. So one of the key things that changed 15 years ago is that people went from sound cards that could do mixing, that could take multiple sound inputs, to much more simple sound devices and expecting software to do everything else. On Linux, Pulse Audio does that, and it does all kinds of things. But it also does more advanced features such as Bluetooth, device configuration, sending audio over the network between machines. It has plugins like echo concession and other effects. And it brought us here for like almost 15 years. So it was quite successful. But a couple years ago, there was a new requirement that came. What about video? What if you wanted to do the same thing that you do for audio, but for webcams? So the idea was to create a project that originally was called Pulse Video, and was basically a way to share webcams with applications that are containerized. This project ended up being given to Wim Taymans, who's the original architect of GStreamer. And he looked at this and spent quite a bit of time doing R&D, and he figured out that really audio and video, they're kind of similar, that you could make a really, really awesome multimedia daemon that handles both video and audio, and that you could even have something that would replace Pulse Audio and Jack from the Pro Audio side, so that the Linux media services could actually be competitive with what you have on other platforms. So so he came up with an architecture for this. One of the main things of this architecture is that it's graph-based. It's not only a single fixed pipeline like Pulse Audio was. Inside the PipeWire system is a graph that can be arbitrarily complex. It can also be multi-process, meaning that although there's a core PipeWire daemon, parts of the graph can actually run in separate processes, providing isolation and security. It uses a simple Jack-like scheduler so that you can have the same performance as Jack. So it doesn't have the kind of complexity that you have in something like GStreamer. But at the same time, it's extensible. So it has a type system that is extensible, where you can carry arbitrary data types. And it has also extensible protocols. So each object in this graph can expose interfaces, and you can create your own object with your own interfaces, meaning that it can be extended to more features. One of the key goals of PipeWire was that it had to be low latency, real-time capable, meaning that for audio, we want to be able to have under 1.5 milliseconds of latency possible. But that's really good if you want to do low latency. But if you're doing regular desktop class multimedia, you're just playing music, you actually want a much higher latency to save power. And so PipeWire was designed to be able to accommodate both by adapting the latency to the needs of the client that are connected. One of the other key differences from Pulse Audio is the presence of an external session manager, meaning that the PipeWire core itself doesn't have any policy. It doesn't have any smarts. All the smarts are actually in the external session manager. So what does the session manager do? It sets up devices. So things like DSP processing, mixer, effects. It controls all the security and access control for clients. So when a client connects to PipeWire, it doesn't have access to anything, and only the session manager can give it access, meaning that we can have a different view of the graph from different clients. You can see a different subset. Also, the pipeline manager, the session manager, one of the key things that it does is that it links the nodes of the graph together, creating an actual graph instead of just separate nodes. This is done most of the time automatically, so that your application can just say, I want to play music, and then it will connect it to the appropriate sync. PipeWire itself comes with an example session manager, but it's really an example, right? That was highly specialized for desktop use cases, trying to reproduce the existing behavior of Pulse Audio. To make something more useful for embedded systems, at Collabora, we wrote something called Wire Plumber. It is a session manager, but it's not really only a session manager. At the core of it is a library. It's a library to implement a session manager. This library comes with everything needed to make it into a daemon, and you can write policies as actual code. The example policies that we ship with it are in Lua, and they also implement a desktop-like session because we found that these are often the more complicated. Not complex, but complicated because you have to deal with all kinds of existing applications, unlike an embedded system. That said, because it is Lua script, you can actually write any kind of device-specific policy that you will need. Relatively easy. It's now been endorsed by the PipeWire maintainer as de facto standard session manager, and they're probably going to retire the built-in example and just tell people to use Wire Plumber to build session managers. So this is the architecture, like the overall architecture of Wire Plumber, of PipeWire. At the core of PipeWire is the PipeWire daemon. This is where the core graph runs. The PipeWire daemon is controlled by the session manager, but directly talks to some hardware devices, Video for Linux, ALSA, and talks to some other devices through a socket using MMFDs, event FDs, which I'll explain, so that it's highly efficient. One of the key goals of PipeWire was to provide zero copy with modern kernel APIs. It is dependent on Linux, so it's not portable. And because it uses modern APIs such as MemFD and DMA-buff. A MemFD, for those who are not aware, is a mechanism for the kernel to allocate a memory buffer. And it has a functionality that once you're done filling this buffer, you can seal it. And once a buffer has been sealed, it cannot be modified until there's only one owner to it. So you can seal it and send it over a socket. And as long as there are more than one process that can access this buffer, it's read-only. And once all the other processes have released it, then you can modify it again. DMA buff is also a way to transfer a buffer as a file descriptor, but it's a bit different because DMA buff was really designed for hardware. So it was designed to transfer hardware-specific buffers. These buffers can be in system memory, or they could be in a separate memory, for example, memory specific to the GPU, or it could be like memory that has specific alignment or something like that. It's really been designed to send buffers between pieces of hardware inside the system. So PipeWire supports both. I mentioned it's a bit like GStreamer. That's because it is based on a plugin system. All of the nodes in a PipeWire graph are implemented using plugins. These plugins are implemented using a C library that's really headers, a header-only C library. It's extremely lightweight in data structure, meaning it's really designed for high performance, but it's much more low level than something like GStreamer. This means that a SPA plugin only contains the core algorithms that it implements. It doesn't do things like create threads or push buffers, right? It doesn't have a mechanism to connect to another plugin. This is all done by the higher level, meaning that we could implement different kinds of systems using SPA. Right now, the only user is PipeWire. This is why Wim always says it's like GStreamer, but not so heavy. It's actually quite different. And it has much lower CPU usage than Pulse Audio. If you lower the latency of Pulse Audio, even on a very powerful modern computer, you easily fill a complete core with just Pulse Audio. PipeWire is highly efficient even in the face of very low latencies. So I'll give you some example. A typical desktop use case where you have a 20 millisecond of latency will take less than 1% of one core. If you have a pro audio use case where you have only 1.3 milliseconds of latency, that's very little, right? That's 1/10 of a video frame at 60 frames per second. If you do that with Pulse Audio, it's more than the laptop of Wim can do, right? So the system just cannot do it. In our case, we can do it easily with just 2 to 3% of the CPU. Even if we throttle the CPU to 800 megahertz to simulate a slower computer, we can do 1.3 milliseconds of latency with only 6% of the CPU, meaning that it's actually usable on lower powered embedded systems too. One of the other big advances that PipeWire uses is the Linux-specific event-AVD and timer-AVD systems. This is used to be able to send data between the processes in an efficient way. One of the things that it does, like Pulse Audio, but unlike Jack, is that it can put a device to sleep when open, meaning that it tells the kernel that the devices are not used anymore, and then they can actually be powered down if needed. The next big feature of PipeWire is the security. As I mentioned, PipeWire, it's a graph composed of nodes. But it's also a series of clients. A client is a connection to the PipeWire daemon. And each client can actually has a separate set of permissions. For each object in the graph, the session manager applies permission, and these permissions are specific to a client. So two clients can have different permissions and see a different graph. Right? This is a key security feature, meaning that a containerized application might, for example, only be able to see audio devices, or maybe it can only see one audio device, and that's it. It doesn't know that there are multiple devices, or it can maybe only see the camera but nothing else. Right? This way, appropriate security can be applied. For example, on the Linux desktop, the Flatpak system comes with portals, and these are dbus APIs where applications can request specific permissions, and then these permissions can be granted or denied, often based on some user interaction. So if an application wants to see the camera, you will have the same thing that we can do on modern mobile phones, and it will say the application wants to access the camera when you let it access it. Or if the application wants to share a screen, then you just say, I want to share a screen, and then the system UI will select which screen or which window to share. So this is an example of a graph. You can see that nodes come in two colors. Purple nodes are nodes that are implemented entirely within PipeWire. Green nodes are actually nodes that are also implemented within PipeWire, but are proxy to an application. This is a really nice example because it shows all the different features. For example, if you want to send a video stream from the graphics compositor to an application, the graphics compositor exposes a node in the graph, and so does the application, and PipeWire can forward buffers between the two nodes. So both nodes are actually proxy nodes. If you want to capture from a camera, the Video for Linux node that captures from the hardware is entirely inside PipeWire, but the application exports a node to the graph where it will receive the buffers. The same thing applies to audio. So the audio API. So PipeWire has something called an audio stream. An audio stream takes input from the client and does conversion. Basically, it allows the client to be a bit more simple. So the client can say, I have some specific clock rate, some specific format, and all the conversion is done by the stream to be in the format of the graph. So the graph normally runs in a specific format, and everything is converted to that format when it enters the graph. For me, that format more or less matches what the hardware device that is connected to it. Audio server, right? This is an example of an audio server. So you would have, for example, a media player that's the PipeWire or the Pulse Audio API, or an ALSA application that will use an ALSA plugin for PipeWire, and that will connect to the PipeWire daemon. Their connections get wrapped into a special object that does all these conversions. This is the audio stream object. If you have a native Jack application or native PipeWire application that doesn't use the stream API, then it will see the graph as a raw graph, right, without any conversion. And the application has more control, but it's a bit harder to write. So replacing pulse audio. PipeWire itself, the key developer, Wim, works at Red Hat. And so it has been deployed in Fedora since the last version released 6 months ago. The next version, which we think is going to be released next week, the meeting is tomorrow to decide, will ship WirePlumber as the session manager instead of the example session manager. And this should bring PipeWire there to the next level. It is mature for daily use. I've been using it for 6 months on my main computer. Actually, I'm talking right now to you through PipeWire. It just works, right? If you're on a recent Fedora, you don't even know you're running it. It's completely compatible. There is a Pulse Audio compatible socket. The original idea was to rewrite the libpulse library using the PipeWire APIs, but it turns out to be more tricky than we hoped. So the solution was to just implement the Pulse Audio socket protocol. So you use the libraries from Pulse Audio, and it connects to a daemon that it thinks it's Pulse Audio, but it's actually not. It's a special PipeWire daemon. It has great application compatibility. Everything just works, right? The applications do not know that it's not Pulse Audio running. There's great Flatpak support, and it can even support the Pulse Audio over TCP protocol. So it's completely transparent. It can also replace JackD, right? It's actually a Jack server once you look at it. This is implemented via a replacement library for libjack that implements the libjack API. And the applications think they're just using libjack, but actually they're connecting to PipeWire. Almost all the APIs are there, right? There's a special Pro Audio profile for the card. So cards in Pulse Audio and PipeWire have profiles. This is because many cards and computers have different ways of working depending on what you connect, right? So there might be 3 connectors, but some of the connector might be input or output depending on how you configure it. This is what the profiles do. The Pro Audio profiles gives you a more low-level control that people doing professional audio like. And it supports all of the advanced Jack features, metadata, real-time scheduling, and it has dynamic latency, meaning that it will give you the latency that your applications requests. So if the application requests a very low latency, it will give you a very low latency. But if the application requests a higher latency, it's not going to waste all your CPU with this low latency. It supports MIDI too. If you're on Fedora or any other distribution that uses PipeWire, you can run any Jack program by prefixing it with PWJack, and that will put the right environment variable so that the PipeWire libjack replacement gets loaded and the application just doesn't know. So this is a tool from Jack, completely unmodified, called QJack Control. It shows the Jack graph, but this is actually running on top of Pulse Audio, of PipeWire. So it's completely transparent to the Jack application that it thinks it's Jack, but it's not. And you can see all the normal desktop applications. You can see Firefox running here. You can see there's a docking station. It's a very standard computer. But what you can do is that once you run a Jack application, you can actually put it in the middle of the graph and do advanced audio processing. They're transparent to the application. So Firefox doesn't know it's talking to this advanced thing. It just thinks it's playing, and everything is handled for you. So it works just like regular Pro Audio setup that the Pro Audio people are used to. The next big interesting story is the Bluetooth story. It's really a story about how WirePlumber, although at first it was really one guy, Wim, and then we came in, George mostly came in to help with the WirePlumber. And now it's a big community of many people contributing. So initially, Bluetooth started in PipeWire 3 years ago, when Wim, the original author of PipeWire, just wanted to prove that, prove to himself that Bluetooth could work. And he wrote an A2DP sync. It was very simple, but it managed to play audio, right? And didn't do much more. But at least he was like, okay, check, I can do Bluetooth. Advanced features left to the reader. Not long after, a couple of months after, our team at Collabora, working as part of the automotive grade Linux group, decided to add the other profiles, so HSP and ATDP source. We did some work and we made some progress. And we made it mostly work, but the sun was a bit glitchy sometimes. But at least we had something that was kind of working, and it brought it really to the next level. A bit later, in the summer of 2020, Frédéric, someone else from Collabora, who had a lot of Bluetooth experience, started integrating Ophono and HSP HFPD as ways to get the more advanced HFP profile. He also added support for the MSBC codec to have better quality when using headsets. Later in November of that year, Wim fixed PipeWire again to make A2DP really work this time. On December 1st, the Pulse Audio project rejected a merge request to support HSP HFPD because of personal conflicts between the developers. A huge wave of developers were very angry with Pulse Audio and decided that they would instead make PipeWire really good. So they really improved the HST HFPD support in PipeWire. It was already there, but they made it better. And they added support for all of the other codecs that people expect now: aptX, AAC, LDAC, and SBC XQ, which is just a higher bitrate SBC. With all of these added, a lot of underlying issues were also fixed. So there was a lot of more people using it, so testing it and fixing it. And also, Frédéric, at the same time, because of the idea that having HFP, HSPD, which is a Perl daemon, not be great for embedded, and Ophono is very specific to modems, decided that it would be better to just have a simple HFP, HSP support in PipeWire itself. So with all of this effort, we're in a state now where PipeWire probably has the best Bluetooth stack that we have ever had on Linux. It's always been an issue for the last 15 years that Bluetooth headsets on the Linux desktop were kind of working, but not that great. Now we're really at the point where everything just works. It's the best state that we've ever been in. And I believe that this also will translate to embedded systems. So it means that we have stuff that just works. You can just use it. So that was audio, right? Next is video. Video, in a way, right now is a lot more simple. The main use case for PipeWire up to now, right, before Fedora 34, what everyone else is using it for is screen share. The Wayland protocol, which is replacing X, right, is only about taking buffers from applications and giving them to the display. The problem is that people sometimes want to do remote desktop or screen recording. They want to take what's on the display and give it back to the application. The Wayland developers decided that this was just not in scope for their protocol, for their plans, that people should do it some other way. This is where PipeWire came in. PipeWire really allows an application to share buffers, right, to other applications. And this is all that screen sharing is. So the main compositor that implements this, right, is Mutter, the one used by GNOME. Also, Kwin from KDE also has the same code. So when an application wants to capture a screen, it doesn't just connect to PipeWire and have a screen capture, because if it does, PipeWire will say, I don't have anyone sharing my screen. Instead, it has to connect to a portal. A portal is a dbus interface API that the application connects and says, I want a window. And then this will actually pop a non-screen window to the user, and the user can say, I want to share my whole screen or share a specific window. Once the user has selected that and has approved it, then the compositor will expose a node in the PipeWire graph, exposing the buffers from that specific window or the whole screen. And the screen recorder application will be given a file descriptor that it can use to connect to the PipeWire daemon, allowing it to receive these buffers. The way this is done, obviously, if you have more than one application connecting and requesting the whole screen, for example, we're recording and screen sharing with separate applications, the compositor will not have to send the buffer twice. They're just going to be given once to the PipeWire daemon, and it will do the multiplexing. So that's the story of screen sharing. cameras are very much the same. Remember the original goal of PipeWire was to be a pulse video, right? It was to share video cameras. This is because on Linux, remember the V4L2 devices, once they're opened by one application, the other applications cannot use them. And if an application uses it and just keeps it, then you can never reject it, right? You can never disconnect it without killing the application. That has worked a long time ago, but in the modern system, we expect more. We expect security, we expect controllability, we expect to be able, for example, to transfer the camera to the most active application, for example. PipeWire offers that, right? PipeWire itself opens the device, talks to the V4L2 API, captures buffers, and then sends them to applications. This is really useful because of the next big thing that's happening in cameras on Linux, and it's that modern computers don't just have webcams, right? They don't have cameras that just send you a completely finished buffer. The modern cameras are really a composition of many different pieces of hardware. The sensor is really a relatively stupid piece of hardware. It just sends you a Bayer, a matrix. And then you actually need an image signaling processor. You have a lens that's a separate piece of hardware, right? You have all these different pieces of hardware that need to be controlled together. Up to now on Linux, there was not much of an API for that, but libcamera is trying to bring a standardized API for these kind of cameras. The annoying thing, obviously, is that if you're writing an application, libcamera, obviously, it's a completely different API from V4L2. So although there is a libv4l2 plugin to kind of simulate the V4L2 API, it's another library that's a bit buggy, and it still doesn't help you if you want to share it with another process or if you want to disconnect the application from the camera. Actually, it gives even more control to the application over the camera. So the idea is to put libcamera behind PipeWire so that the application will just connect to PipeWire and use the camera through, for example, either a plain V4L2 or a libcamera, or it could be, because now it is abstracted, the camera could be something else. It could be a network camera, that's actually an RTSP device. And the application would not have to know if it's an RTSP camera, if it's some other kind of device, or a geeky Ether camera, or a good old-fashioned webcam like my laptop. The other big advanced use case that we expect is something like Siphon for Mac, which means it's a processing plugin that you can put in the middle of your video pipeline, for example, to have funky effects. The other feature ahead is improved security. I talk a lot about the security, but in practice on the desktop, most of the work right now has been focused on replacing pulse audio. And in pulse audio, there's no security, right? That's actually one of the original impetus of all this work, was to add security. But in practice, the security is not implemented in the session manager, right? The session manager gives all the desktop application full access. And this is an area that will be improved. The mechanisms are there, and now it's just a matter of writing the policies and making them work with existing applications. That's quite a challenge. The other thing that is not very strong right now are non-desktop use cases. So we have all the mechanisms in PipeWire to write these policies. Non-desktop use cases are obviously a bit difficult because every single embedded system is different and unique. But we're hoping to create at least some examples. We're starting with automotive because automotive seems very complicated, like multiple cameras and things like that. And they have safety critical parts and non-safety critical part, right? You might want to capture from a camera and send it to the self-driving computer, but also send it to the screen, right, for the user, which actually an entertainment system, which is not secure. So we're trying to build these kind of example policies, but we expect people building these kind of devices to end up writing their own policy. What we hope by having these example policies can make everyone's life a bit easier. So that's what's upcoming in PipeWire. Thank you, and now I'm ready for your questions.
Thank you so much, Olivier. We have a few questions already in chat. Let's take the first one. Does PipeWire take advantage of the new unified memory, which is kind of shared between CPU and GPU?
Well, so PipeWire itself does not actually know about this, right? This is really done at a lower layer. As long as you use something that can be exported and imported as DMA buffs, then it should just work. So this is now that NVIDIA has basically folded and accepted that GBM is the future. This really applies to every single device that we have out there. So yes, you can make it work.
Okay. We have another question. Says, any special capabilities PipeWire brings for multimedia device connected distributed scenario compared to Pulse Audio or any other competing open source frameworks?
So when it comes to connected and distributed, it's an interesting question. Right now, the decision, well, the logical idea was that PipeWire itself would not know anything about the network. So we have the separate process. For example, Pulse Audio, Bluetooth is actually a separate process, but it means that we can also write these separate processes to be a different protocol. For example, right now there's nothing to share a camera, right?
Right.
I would definitely like to write an RTSP source so that you can have your RTSP camera, like a professional broadcast camera, for example, integrated.
Okay. Okay, we have another question, which is actually 3 questions put together. The first part is, what is the memory allocation mechanism for shared mechanism?
So it depends which kind of memory. So if it's device specific, then the memory is allocated by the device driver and exported as a DMA buff. So it's a file descriptor that we share. If it's an MFD, it's a special Linux API to allocate these MFDs. And this is just kmalloc inside, right? It's just regular memory.
Well, the next part is, will there be any interface for fast audio path like in Android?
So this is actually something that we have been working on very recently with our friends at Valve. So this is something that's actually upstream now. There is now a fast audio path that does not do any conversion, assuming that the application generates sound in the same format as the sound card. So this is typical for games, for example, right? It just generates sound from software, so you can just generate in the right format, avoiding any conversions.
Also, where do we see PipeWire in 2 years? Can it replace completely Pulse Audio? And currently the documentation support is very less. When can we expect to have the docs more details on supported features and planned features?
So to be honest, so I expect it to replace Pulse Audio. I don't know how fast, but many of the Pulse Audio developers are actually on board with PipeWire. So it's really seen as the next generation of Pulse Audio by many of the core Pulse Audio developers. As for, what was the other question?
Yeah, so currently the documentation support is very less.
Yes.
When do you think it will be updated?
So it's being improved slowly. This is an open source project, so the way the Pulse Audio documentation became so good that a lot of people contributed, and it would be really great if more people contribute to the documentation here. I know that over the last 2 or 3 years, the core PipeWire developers have been laser focused on actually making it work. Right. And the documentation was always a bit out of date because they were changing things quite quickly. But now that we've gotten to a pretty mature state where all the features are there, it's really adding to the edges instead of modifying the core. I think it's a good time to write documentation. And I know the core developers will write some, but it's a different skill, right? Writing C and writing good documentation are very different skill sets.
Absolutely.
And people will appreciate the contributions.
Yeah. Okay, we have a couple of questions. We have time for the questions, so let's just take them. Any CPU usage overheads in comparison with Pulse Audio?
So I had a slide here. It's so.
Olivier, just a moment. Can you just minimize the participant window to your right, because that's hiding the last part of the slide now.
What? Sorry.
Yeah, I could just minimize that. Yeah.
What's the minimize?
The first one. Yeah. Yes.
Okay. So basically, for this example, At low latencies, pulse audio is just unusable. The CPU usage is sky high. For PipeWire, it's much lower at lower latencies. At higher latencies, there's not that much difference because pulse audio was quite efficient. It was really designed for higher latencies, right? So I expect PipeWire to be as efficient as you can get for this kind of use case, and simply more efficient in pulse audio as you lower latencies.
All right. There are a couple of more questions. How does Tiny ALSA work on mobile phones, considering multiple ports for input and output?
So as far as I know, no one has ported PipeWire on top of Tiny ALSA. I might be wrong. But we definitely support complex audio devices. That's one of the key use cases on the automotive side, where they have actually the audio device is actually a DSP that does more processing. And one of the big features that we have with WirePlumber is that you can control or at least talk to these external, more complex devices, right? So let me find this graph. So on the right side here, right, these nodes can be actually quite complex and can expose hardware capabilities. And it means that if you have multiple inputs, multiple output devices, you can expose them correctly and then write the policy on top of it.
There's one more question that we have in the Q&A, and it says, how easy would it be to port a framework or application written based on Pulse audio libraries to PipeWire?
So you don't actually have to port it because we have this thing called PipeWire Pulse, which exposes the Pulse audio protocol. So right now I'm talking to you on the Zoom application, which is a proprietary application, which talks to Pulse audio, and it's on PipeWire, and it doesn't even know, and it just works.
You'd be happy to know that even I'm on PipeWire using my Bluetooth headset on an Ubuntu 18.04 laptop.
Sorry?
I said that even I'm using PipeWire right now on an Ubuntu 18.04 laptop with my Bluetooth headset.
All right, and it's working well for you. Good for you, I hope.
I've been using for the last 6 months. That's the only way I could get my Bluetooth working on 18.04.
That's amazing.
So it works. We know it works. And thank you so much, Olivier. Over to you, Fatima. I think that's all the questions we have for now.
Thank you.
Sure. Thank you so much, Anvit, for that extremely well-structured, Q&A that you just moderated for us. Thank you so much once again. A hearty thank you and lots of gratitude to you, Mr. Olivier, for setting context and introducing us to PipeWire and beginning our first session of day 2 with a lot of energy and a lot of information and education, of course. Thank you so much once again.